Hello and welcome to this video. In this video, we're going to start the thermochemistry unit based on the Alberta program of studies. This first lesson we're going to look at introduces us into the study of thermochemistry and how thermochemistry is used in our everyday lives. So first of all, hydrocarbons. Hydrocarbons are very important in our daily lives. Remember, a hydrocarbon is a compound that has hydrogen and carbon. Okay? It can be any number of them, such as glucose, which is C6H12O6. And glucose is important in our bodies and in all living organisms in order for cellular respiration to take place. And we will review the process of cellular respiration in further videos. Gasoline and natural gas. Natural gas is methane, for example. These are, again, hydrocarbons that get used in our daily lives for fueling our vehicles, heating our homes, we cook with them, and so on. So hydrocarbons, again, very important source of energy, and thermochemistry is the study of energy. Now, it's important to note that this energy that's stored in the chemical bonds of the hydrocarbons originates from the sun, okay? The reason it's originating from the sun is because hydrocarbons come from dead plants and animals that were trapped under rock formations for millions of years, and all those plants and animals originally came from plants gaining their energy from the sun during photosynthesis, okay? The animals ate the plants, converting that energy again during cellular respiration, and so on. So if you are given a diploma question like as follows, the original source of energy stored in fossil fuels, such as methane, the answer would be D, the sun. Okay, common question. Might not be a standalone question, comes commonly up on the diploma in the first few questions. Might have like a two-part question to it where the sun is one of the answers. Now there's two types of fundamental energy in chemistry that we focus on. One is kinetic energy, and kinetic energy is the energy of motion. And we're specifically going to be talking about the motion of particles. And this is measured through temperature. Whereas potential energy is the energy that's stored in chemical bonds. During a chemical reaction, bonds are broken, bonds are formed. And in that process, there can be energy released, energy gained, and it gives us some stored energy that can get used when the compound is broken down in a later reaction. So there are a couple of laws of thermodynamics that we can discuss that applies to chemistry. The first law says that energy is constant. So it can only be converted from one form to another. It cannot be created or destroyed. So the total energy of the system is always conserved. If we are ever what we call losing energy, that energy has still been converted 100%, just maybe not into the useful form that we want it in, which we'll talk later about when we get into efficiency. The second law of thermodynamics says that in the absence of energy input, a system becomes more disordered. That has to do with entropy, and not a topic that we talk about in Chem 30. But what you need to know of this law is that whenever heat is transferring, it's always transferring from the hot object to the cooler object, right? When the molecules have more energy, they are hotter, they're moving around more, they collide with the cooler object, making its particles move faster. So it heats those particles up as the hot object loses some of that energy in the process. So the first section that we're going to look at today involves temperature change. So again, remember, when you change the temperature, temperature is a measure of kinetic energy. The faster the particles are moving, the higher the temperature, the higher the kinetic energy. Okay? Kinetic and potential, like I said, are the two main focuses of energy that we look at. When we have a temperature change, that's a change in kinetic energy. Now, if I want to measure the quantity of that energy needed to either heat up or released when a substance cools down, I need to know the amount of substance, and we're going to deal with it in terms of the mass in grams. We also need to know the change in temperature. Obviously, if you have a bigger temperature change, it's going to require or release more energy. Then it has to do with the type of substance. There's something called specific heat capacity. Specific heat capacity is the heat required to change the temperature of 1 gram of a substance by 1 degree Celsius. Okay, so this gives us the following formula. Q equals mc delta T. The Q, again, I've read in textbooks that one way of understanding what Q means is the quantity of heat. Okay, but if you're asked how much energy is gained, how much energy is released, how much heat is being transferred, that all refers to the Q of the formula. Okay, and you will get an answer in joules when you're using this formula. Your mass, always in chemistry, needs to be in grams. The temperature change will be in degrees Celsius. And the specific heat capacity, as we mentioned, that is C in the formula. Okay? The specific heat capacity, again, is measured in joules per gram degree Celsius. And if you look in your Chem 30 data booklet, that again you have available to you on all of your quizzes, tests, and on the diploma, I believe it's on page 3, that there is a list of compounds, or elements, I should say, substances, with their specific heat capacities. So for example, water. Liquid water. Liquid water has a specific heat capacity of 4.19 joules per gram degree Celsius. So this means if I want to heat up 1 gram of water by 1 degree Celsius, I need to add 4.19 joules in order for that to happen. That's actually a relatively high value. The higher the specific heat capacity, that means it's going to take longer to heat up and longer to cool down. And this is another type of question that you could see, we'll just put to change temperature. Okay? This is a type of question you could see on the diploma that again might talk about, I have 2 different substances that are experiencing the same amount of energy input or output. How are their temperature changes relative, right? So if it has a higher specific heat capacity, it's going to go through a lower temperature change, getting the same amount of energy. That's something that has a lower specific heat capacity that'll heat up quicker and have a greater temperature change. So let's look at using this formula. Find the heat required to change 2.50 grams of water from 10 degrees Celsius to 27 degrees Celsius. So it's asking us for the heat. That is the Q in the formula that we're looking for. It gives me my mass in grams. I'm just going to label that with an M. And this is the temperature change that we're going to go through. And again, my substance is water. Those are all the key things we need for this formula. So I know the specific heat capacity of water, like we just talked about, again is in your data booklet on page 3 for common substances. If it's not in the data booklet, the question's going to give it to you or you're looking for it. And again, I have my temperature change. I could solve for my temperature change separately or just put it into the formula as it is. But if I want to calculate it separately, I'm going to take my 27.0 degrees Celsius and subtract my 10.0 degrees Celsius. And that gives me 17.0. You always want to be consistent with your sig digs. Okay? I mean, when it comes to a calculation, basically once you get your answer, go back to the original question and look at how many digits are in the numbers that you're using that are not considered a counted number or a constant, and that's the lowest sig digs you want to keep. So if I use my formula, Q equals mc delta T, my mass again is 2.50 grams. My specific heat capacity is 4.19 joules per gram degree Celsius. And sometimes I actually make a big line out of this, just for a unit analysis purposes, okay? There's no numbers on the bottom of this fraction. It's just to look at how my grams will cancel and how my degrees Celsius will cancel, leaving me with the units of joules, okay? So grams cancel because they're on the top and the bottom. Degrees Celsius cancel because they're on the top of the bottom. There's no number on the bottom that I have to divide by. I just, in my calculator, I'm going to put 2.50 times 4.19 times 17.0. Okay, So if we pop that into our calculator and follow along and do this calculation with me to make sure you know how to put it properly in your calculator, you'll get an answer of 178.075 joules. Remember again, the unit that is left on top is the unit of my answer. That's why I use that sort of fraction method to show what happens. Okay? Now, sig digs. I go back up at the question. There was 3, 3, and 3. So I can have 3 total digits in my answer. Now, I always keep, obviously, the first 3, and as long as I'm not cutting off the decimal, which I'm not, the decimal is within those 3 digits, I do not need to put it into scientific notation. I just cut it off. I'm cutting off a 0, so it doesn't round the 8 up. If I was cutting off a 5 or more, it would round that last digit that we're keeping up, but I'm cutting off a 0, so it doesn't. So the final answer, our heat required, or our Q, quantity of heat, is 178 joules. Okay? It's a pretty straight 3-variable formula. Just make sure, again, you're putting it in your calculator properly. Make sure you look up the data properly. Always double check your work to make sure you have everything done correct. Let's look at another example. Let's say you're told that 350 grams of ethanol is releasing energy, and it gives us the amount of energy. Now, I want to take a moment to think about what that word releasing means. That word releasing means that it's going to lose energy. And when something loses energy, the temperature is going to go down. Okay? I'm dealing with ethanol, and so ethanol's specific heat capacity is not in the data booklet, so it gives it to you in the question. Now, it is asking us, if the final temperature is 20, what was the initial temperature? So it's important to note that the initial temperature is going to be higher than 20 degrees Celsius, because it's cooling down, okay? So this is kind of a multi-step question where I am actually going to solve for delta T. Delta T is what I want to look for in my formula. So reviewing how to rearrange a formula, the delta goes with the T, right, because that just means temperature change. So I want to isolate for delta T, which means I need to divide both sides of the equation by M and C. When I do that, it makes them cancel on the right side of the equation, and I'm left with a formula, if I rewrite it, as delta T equals Q divided by MC. Now, when you're doing this in your calculator, whenever you have 2 numbers in the denominator, it's really important you put them in brackets so that it does the calculation properly. So if I look again at doing this calculation now, I have 29900 joules as my Q, and I'm going to divide that in brackets by my mass, 350 grams, times my specific heat capacity, 2.44 joules per gram degree Celsius. Now, there's a rule in math, and I'm not a math teacher, so I can't fully get into detail, but when you have units that are going to be in the denominator of the fraction, it actually makes them move up to the numerator. Okay? And you'll commonly see me do that, especially if you're doing molar mass calculations, the mole calculations. You'll see me put the units that were in the denominator here of the denominator of the overall calculation on the top. The reason I do that is because, like I said, when I'm doing unit analysis, which you should really always do in chemistry, you're going to cancel what's on the top and on the bottom, and then the units that you're solving for should always be left on the top of the fraction. Okay? So if I'm solving for temperature change, my degree Celsius should be on top. So when I do this calculation, and again, try along with me, 29900 divided by, open a bracket, 350 times 2.44, then close the bracket. And you should get an answer of 35.011, so on, degrees Celsius. Okay. This is not my final answer, right? This is my temperature change. It wants to know what the initial temperature was. And like we talked about, the initial temperature has to be higher than 20. Okay, so what that means is in order to find the initial temperature, I'm going to take the final temperature and add the temperature change. Okay, if this question were asking me for the final temperature, I would subtract the temperature change because it's going down. But the initial temperature has to be higher, so I have to add it to the final temperature. Okay, so just kind of some theory work you're doing to figure out, again, leave this answer unrounded, by the way. When you have a multi-step question, always leave a temporary or a intermediate answer unrounded. Save it in your calculator, use the whole big number, and then apply it to the other number you're adding it to. So here we get 55.011, so on, degrees Celsius. Now, this is our final answer. We just have to round it to sig digs. So I have 3 total digits in my mass, 3 in my temperature, 3 in my specific heat capacity, and 5 in my energy. I go with the lowest, which is 3. Remember, for sig digs, all digits count except for leading zeros. So if I can keep 3 digits, I'm going to cut it off right there, which again does not cut off a decimal, so I don't need to put it into scientific notation. It would just be 55. Again, I'm not cutting off a number that's 5 or more to round the 0 up, so it stays as 55.0 degrees Celsius. I always recommend putting a box around your final answer. And that is the final answer to this question. I believe there is a sample diploma question. So for the sample diploma question, we are, again, whenever you're doing a numerical response question, always look at the units that it wants your answer in. That kind of tells you what you're looking for. And it is saying it wants to know how much energy this mercury thermometer absorbed. Okay, so that's reminding you I'm looking for Q of mercury. So I know my formula for Q is mcΔT, and I'm solving for Q. I don't need to rearrange the formula. I have my mass. I have temperature change. It's starting at -38 and it's heating up to -13. And the heat capacity, again, is given because it's not in the data booklet. When I'm doing temperature change, I don't want a negative value when it comes to asking for how much heat is absorbed or released. We want an absolute value. So negatives and positives will come up as being very important in this unit in the next lesson, but for now, I'm just always going to take the higher temperature and minus the lower temperature to get like an absolute value temperature change, okay? So -13 minus -38. That's how I'm going to find my temperature change. So if you did it the other way and you got a negative temperature, just leave it as, again, an absolute value and use the positive answer. So 25.0 degrees Celsius is my temperature change. Okay, so if I plug those variables in, my mass, again, 1.02 grams. My specific heat capacity is 0.140 joules per gram degree Celsius. Remember, again, I'm just showing the units there. There's actually no number that I'm dividing by. And my temperature change was 25.0 degrees Celsius. Now, unit analysis, like I said, some teachers might make you do it. I prefer my students to do it, but if they don't, I don't dock marks. Okay? So I'm going to get left with an answer in joules. If I do that calculation, again, I have 1.02 times 0.14 times 25.0, and, oops, I made a mistake somewhere. 1.02 times 0.14 times 25, there we go. And we get an answer of 3.57, that's the only digits it has, and 3 digits is what my answer needs to be recorded to, because again, I have 3, 3, 3. And the specific heat capacity is an example where there's a leading zero. It doesn't count for sig digs. Those are my sig digs. So I can have 3 sig digs. Again, my answer needs to be in joules, which it already is. So all I need to do would be to record that through, and the numerical response questions on the diploma will also tell you how many digits to record your answer to. So this is my 3-digit answer. The decimal does not count as a digit, so the 3 digits is the 3.57. When you're recording this, though, in the numerical response section of your test, it'll have 4 boxes, don't mind my horrible drawing, and I would put 3.57 in the boxes. So it would take up all 4 boxes. Remember to always circle in the numbers as well in the bubbles, because that's what the machine that marks the diploma reads. So don't just put the numbers, also circle in the bubbles. And I believe that is it for this lesson. Thank you very much for watching.